Okay, we're going to do top head at the end. Here we go. So let's get started. So what we're currently working on is the approximate accumulation function. I'm recording. Here we go. So this is the approximate accumulation function. All right, let's get all that stuff in. Okay, so you guys, so here's what we'll do. For lecture, when you're turning in homework, fold it up, put the heading on before you come to class. Have it in your hand, and then when they collect, you just pass it in. So it doesn't take 2 or 3 minutes to do it, okay? So just have it folded, have your heading on before. Don't do all that stuff when class starts. Okay, so here we go. We're working on the approximate accumulation function. This is the general structure of it. So here's the deal. There's kind of the big picture, and then there's details. And when you inject all the details into this, it gets very scary. It gets very overwhelming, like what you saw maybe in chapter 5.1. With all the details involved, it's scary. But you can't... All right, are we ready to start? Is everyone listening? This is super important. Okay, so... Okay, here we go. So we want to talk about, when you look at this, can you whisper? Cerny, can you whisper? Okay, so when you look at this, we want to talk about what you should understand as the big picture of it. What's the most important about it, okay? And not like the details kind of come to the forefront and scare and like overwhelm you. So we're going to be filling in some of the details today, but let's start by really talking about what this thing means, okay? So this thing is primarily about 2 key principles. There's really 2 major things going on here that we have worked on hard for the last month. And the first one is this. The change in the dependent variable is equal to the constant rate of change times the change in the independent. Okay? So... you're driving, everyone listen, you're driving at a constant rate of change of 60 miles per hour. How far will you go in 2 hours? 120 miles. You just did that. Okay? You just did that because you took the constant rate of change of 60, you multiplied by 2 hours, and you got 120 miles. So you just did that. Okay? Otherwise known as what? What is this? What's our mathematical notation for this? Good. dy equals mdx. Change in dependent is a constant rate times change in independent. Okay, so where does this appear in our approximate accumulation function? Yeah?
Right in parentheses of R. You either want to have it
Inside the parentheses of R? No. Not inside the parentheses. Yeah. You looking at the left, the summation term there? Yep. Right. This is the first where it appears. For every we calculate the change in the dependent for every completed interval. There it is. See it? Constant rate times a change in x. Constant rate times a change in x gives us an amount of accumulation in each completed interval. You see it? That's all that is. Okay? That's all that is right there. Okay, anywhere else? Does it show up anywhere else? Yeah, where? Okay? Right. Within the current interval, you have an amount of change of the dependent variable calculated the same way. Constant rate times dx. So basically this whole thing is just summing up a bunch of these. The whole equation just boils down to summing up. M dx plus m dx plus m dx. All the completed intervals, plus then the partial, the smaller, with the current interval, within the current interval. Okay, good so far? So that's really what it boils down to. But so there's one more thing. And the second principle is this. that the final value of a dependent variable is equal to the initial value plus the change. Should make perfect sense, right? So you have some value of a quantity, if you add on the change, you're going to get a new value of the quantity. Where does this show up? How does this principle show up in the approximate accumulation function? So where do we see initial value of dependent plus change in dependent? Where do we see that there? In the hat.
Initial value is like the summation, the sum.
Right? Yep. So he's saying the initial value, okay, so here's the mathematical way to say that. Y final equals Y initial plus dy, right? Y final equals Y initial plus dy. And so he said the initial value is that whole summation there, right? This is what has been accumulated over all the completed intervals. And that's like when we come to the current interval, that is our Y initial, or our total accumulated amount, our starting Y. Okay, and then where is dy? What does dy have to do with here? The change in the dependent variable. Well, it's right there, right? So you have the total amount accumulated so far plus the change that's accumulating within the current interval. So that's like a fixed amount plus this changing amount within the current interval, totaled up gives you whatever that final amount is, which is changing, right? The final amount changes as you progress through that current interval. So what does this have to do with that equation? Well, it is that equation, right? This is your... Let's see. Backwards. This is Y initial plus change in Y. Okay? Okay, does it make sense? So whenever you're working with this thing, this has to be solid, okay? There are like 3 more details that we're going to plug into this, and I feel like when those details are in place and you're trying to understand the whole thing with the details, it's just a mess. It's like so confusing. But this has to be, you should be able to attain pretty, given what we've done so far, that we've worked hard on these 2 principles, you should see them very clearly at work there, kind of creating this function. Questions? Anybody have a question? Okay, so watch that part of the video over and over again until you have it. Okay, so let's kind of apply this and practice this and then the second half of class we're going to work on. Like I said, there are some details we have to fill in, but let's keep practicing the big picture of this. Okay. I got a situation here of unloading sand onto a scale. Okay? So this function is showing the rate of change of weight as a function of time. This is showing the rate of change of weight as a function of time. So this is we know how fast something is changing at every moment. We know how fast something is changing at every moment. Our goal is, how much do we have at every moment? Okay? How much do we have at every moment? Okay, so how does the sand unload? According to this rate function, how does the sand unload? At first, how does the sand fall off the truck onto the scale? Quickly at first? No, slowly at first, right? The rate starts low, right? And then as time goes by, at around 2 or 1.5 seconds, the rate is high, right? So it's coming off slowly at first, and then it's coming off very quickly, and then towards the end of the 3 seconds, the rate slows down again. Okay, so, and you can imagine, if you dumped a truck, that's kind of how it would be, right? You'd have a little sand at first, and then most of it would fall, and then there would be a little bit left at the end, falling off, right? So that is showing that rate of change. Okay, so I have some questions for you. And then we can look at consider this. So what are we doing? So we know that in order to start building our accumulation function, we need constant rates, right? Constant rates over moments, right? Over moments. So here's a scenario. So just take a couple minutes to answer these review questions, okay? So what's the dependent variable quantity of focus? What's the independent variable quantity? And then what is the animation showing for, so answer questions 1 and 2, just take maybe 3 minutes, just kind of a review, just to get oriented to this situation. Go. Okay, what is our dependent variable? What are we accumulating? That's what I'm saying. So what is the dependent variable accumulating? Pounds. Pounds of sand. Pounds of sand. Which axis is that going to show up on which graph? Is it going to be y or x or y, on the left or the right graph? Y-axis on the right graph. Okay, over here. This is going to be pounds of sand accumulated, right? The y-axis on that graph is rate of change of pounds per second. Okay, what's the independent quantity? Time in seconds. And where does that show up? Which x-axis? Both. Right and left. Same x-axis quantity for both. Time in seconds on both. Okay. What's our starting value accumulation? A. Here. So where are we starting according to this animation? 0. X equals 0. Okay. What's duration of a moment? 0.3 seconds. Okay, so if we were, that purple line is showing 0.8 seconds. That vertical line is showing, say, if you were to pause the accumulation at 0.8. So here are the questions about that. How many completed intervals? How many completed intervals if x is 0.8? 2. 2. 1, 2 completed intervals. What defines the start and end of the current interval? 0.6 to 0.9. Okay? And then what's the value of dx? What's the value of dx? Okay, so dx is always varying within the current interval from 0 to delta x. So it always varies within the current interval from 0 to delta x. So when you start a new interval, dx starts over at 0 and then varies to delta x and then starts over again and varies to delta x. And then starts over again, 0 and varies to delta x and then starts over. It's always varying between 0 and delta x in the current interval. So in the current interval, from 0.6 to 0.9, what is dx if x is 0.8? 0.2. Does it make sense? So as I've talked to some of you working your homework, this idea of dx, wasn't solid with most people I talked to. Dx is in the current interval, and it varies from 0 to delta x. And then once you get to delta x, you start the next interval. Dx starts over at 0 again and varies to delta x. Next interval, 0 to delta x, okay? Is that better? There's a video. So there's a little animation in the textbook. You can watch for that. Okay, what's the value of left x if x is 0.8? It's the x value at the left side of this interval. 0.6. Left x will be the x value at the left side, or the starting x value of the interval. And why is that important? Why is that important? Yeah.
Because you want to know if you are actually in the interval, or if you're starting a new interval, if your point is going to be at that new interval, or that is within that.
Not quite. Why do we need? So look at. So left x is 0.6. Why is it important? For the rate function. So it has to do with the rate function that we're building. Why is left x important? Yeah.
That's the that value of left x is the value for the x value of the rate of change function on the interval.
Right. That's the. We're going to use the rate, the actual rate at the left side of the interval to be the constant rate for the whole interval. You see that? So where did we get this constant rate? We got it from r of what? R of 0.6, or r of left of x. So this constant rate for the current interval is r of left of x. That's why left x is so important, because it allows us to get that constant rate in the current interval. So yeah, so this is r, right here, this rate, butterfingers today, r of left of x. That's that constant rate right there. Okay, questions on these warm-up questions? So now we want to talk about how this thing gets built, okay? How does this thing get built? So we're going to talk first about, just look at the first interval. I'm going to change the n just to be showing from 0 the first moment. Okay, so we're just going to be focusing on this first moment, and I'm showing it over and over again, the first moment. What will the accumulation function be in that first moment? So I'll set you loose here. So consider x changing through the first interval. That's what I'm showing. X is only changing through the first interval. Write the rule for the accumulation function, and then relate the rule to this. Okay? What are the relevant values of j? The summation of r delta x and r dx. Okay? So take a minute and see how you do on this. Okay? So just in the first interval, write the rule for the accumulation function and relate it to our fx function. So in this first, it's just increasing at a constant rate. At what constant rate is it increasing? R of 0. R of 0, or R at the left side of the current interval. So it's increasing at R of 0. And so to get the total, to get the amount of change in pounds of sand, it'll be R of 0 times. Okay, it won't be 0.3 because it's a changing amount. It's a function of whatever amount of time has gone by. So R of 0 times 0.3 would be the total amount accumulated in that interval. We want the function. We want the function. So R of 0 dx. And how can we rewrite dx? So R0 equals, or sorry, R0 times, how can we rewrite dx then? So dx is the distance from the start of the interval to the current value of x. So what is dx? Final minus initial. Final is current value of x. It's changing. Initial is left x. That is the rule for the accumulation in the first. And since it's constant rate of change, it's just going to increase constantly. So there it is on the right. Okay, so as that constant rate plays out for 0.3 seconds, we get a constant accumulation of sand. That's a constant slope to that line, right? Of R of 0. Okay, so now, what are what about the sum of R delta x? We'll start there. Sum of R delta x. What is it? It's the summation for the completed intervals. And what is that right now? Our current interval is interval 1. There are no completed intervals. 0. Okay? So this, for first interval, this whole thing doesn't exist yet. There are no completed intervals yet. It doesn't exist. So there are no relevant values of j. Okay? Because j will count through the completed intervals. Okay? So there are no j, it's a 0. And so then this is what we have in the first interval. All we have is this part, which we did. So that's right there. R sub 0 dx. So when we're in the first interval, we're just looking at that right there. That's our function. Does that make sense? Okay, so let's jump to the third interval. So I'm gonna jump to the third interval here and have you answer the same question. So we'll go third interval, and then I'll turn off the, just show, and from the third interval starts where? 0.6, ends at 0.9. Let's see what that looks like. Okay, so here we are in the third interval. And we're going to work on this, understanding what's happening here when the current interval is the third interval. Okay, same questions. Number 3, go. Third interval. Yeah. Yeah. Yes, it's always the distance from the left side of the current interval to the current value of x. It changes. So, yep. Final is the current value of x. Initial is the left side of it. Final mass initial. So, okay, so I've answered question B. Look at what I wrote and talk about what I wrote. That should make sense. Make sense of what I wrote in blue, okay? Keep talking. Yeah. It's saying add up a sum plus a sum plus a sum. The summation side means add a bunch of these together. There's only one. No, it's right there. Just one. It's going to say, let j equal 1, get that. And let j equal 2, get that. Now add those together. That's what the summation side says. You're not adding a bunch of sums. You're adding a bunch. This says sum up a bunch of these. It'll be the total number of completed intervals. So this will be 2. Right now it's 2, but as soon as we move into the next interval, it'll be 3. We haven't done it. Yeah, we're going to do it today, hopefully. No, we haven't made yet. No, the bottom number tells you where to start. If j takes on every value, j takes on 1, and then j is 2, and then j is 3, and then j is 4. takes on all the values from here to here, and then we sum all those up. Okay. All right. So, in talking to people in this week, my feel is that this summation thing is really confusing. That people are having trouble with summation. Okay. So what this means is, this is just a way of saying we're going to sum up a bunch of these things over and over again. We don't want to keep writing out, because if there were 50 completed intervals, we don't want to write this thing over and over 50 times. They all look alike, right? They all look really similar. So can't we just write this once? Let's just write this once and then have a way of denoting that we're going to just add that over and over again, however number of times. So how many terms do we have when we're at the current interval, it's the third interval? How many things are we going to sum up with a summation sign? 2. We're going to have an r delta x when j equals 1. That's the first completed interval. So this is j equals 1 right here. So j equals, this is 1. And we'll get that total amount of change. R0 times 0.3. Complete, right? Complete. And then j equals 2. And so we'll get r of 0.3. It's a new constant rate, but for the same amount of change of x. And that's when j equals 2. And so then this summation says, add those together. Add it together when j equals, get the value for when j equals 1, get the value for when j equals 2, and then sum says, add them together. So does that make sense, what I wrote? Yes, please.
So when like for this example, if it's 3, we're trying to find that third interval, would it say j equals 3 under summation?
No, it'll always say 1. J starts at 1, starts, the first j. And then this is going to be, this number up here will be the last j. And then what it means is you're going to let j be every number in between the first and the last, and that each one of those will give you a term, and you're going to add all those up. Is that better? J will always be 1 to start for this function. It represents the first complete interval. And then j will be 2. That's the second complete interval. And then j will be 3. That's the third. And then you're going to add them all up. And then the last j will be the last completed interval. So for this example, in the current interval being the third interval, j will start at 1 and it'll end at 2. And there'll be 2 terms to add together. So when we're in the 37th, current interval is the 37th interval. J will start at what? And we'll end at 36. And you'll add 36 things together. 36 r delta x's together. For j equals 1, for j equals 2, for j equals 3, for j equals 4. Okay? And then we're going to add on the changing amount of accumulation in the current interval. And that's this right here. So this adds up all the completed intervals in one step. And then this adds the additional accumulation in the third interval. So let's turn on. So what will that look like? Over here? Shouldn't have written down there. But, so, completed interval, complete interval. So right here, this y value right here, that y value right there, is the summation. The first term in the sum. The summation r delta x. Because it's all the total sum of weight of sand for all the completed intervals, or y starts, right? Y start plus delta y, plus dy, which is this changing amount to get the current amount of weight for whatever x is. Okay. So is this better for understand? So are we understanding this formula better? Can you ask a question that will help make it even better than that? Anyone have a question? Yeah.
More or less, when you're moving from interval to interval, you have to include the previous interval plus changing the.
Yes. So as you move through the intervals, this will calculate the total accumulation from the completed intervals. And then we have the additional accumulation in the current interval, and that's variable, right? That's varying. And that's why this is a function, so that we can get the total amount of stuff at every moment, right? And then when this interval gets finished, now we have one more in here. We have one more completed, and we start the next interval. The next interval starts. And when that one finishes, we get one, there's now one more completed, and then the next interval. Is that up? Okay. Other questions? Okay, so this dx right here is x minus left x, right? We talked about that a few times. Dx is always in the current interval. It's the distance from the left side of the interval to the current value of x, which is changing, right? That's a variable, that's changing. Okay? And then this number right here is what? No, just in general. Total number of completed intervals. Right? It's like the last j. So j equals 1 will always be the first j, and then j equals this is the last j. No, it depends on your delta x. Okay, no, but it depends on what your delta x is, right? If I make delta x smaller, then it could be a lot more. Okay? All right, so, time for. Let's take a look at how do we get, so what is this right here? This input into R is the starting value, starting x value of a completed interval. Okay, good question. So which one is it? So this sum is for all of the completed intervals. So it's really the starting x value of the jth interval, right? So as j changes, that's going to change as well. So it's the starting x value of the jth interval. So let's take a look at that. How do we get the starting x value of the jth interval? Come on. Okay. So here are the intervals. J equals, this is the first, this is the second, this is the third, this is the fourth completed interval, the fifth, the sixth, and the seventh. So suppose we're in the current interval is the 8th interval. So I'll back it up a little bit here. All right, so we're in the current interval is the 8th interval, so our completed intervals are 1 through 7. 1 through 7 are the completed intervals. And so if we come out here to like interval 4, okay, look at interval 4. What do we need? J equals 4, and we need this x value right here. Okay? We need that x value right there for the 4th interval. Here's the 4th interval. So x is, at the beginning it's a, and then how many intervals do I have to go over to get to the left side of the 4th interval? 3, right? So it's going to be a, this x value will be a plus 3 delta x. Do you see it? If I start at a, whatever a is, and add 3 delta x's, I'll get to the left side of the 4th interval. Do you see it? And what if I want the left side of the 6th interval? The left side of the 6th interval would be a plus 5 delta x. So therefore, the left side of the jth interval is always a plus how many delta x's? J minus 1, right? We said in the third, if it was in the fourth interval, I needed 3 delta x's to get to the left side of the fourth interval. If I'm in the sixth interval, I need 5 delta x's to get to the left side of the sixth interval. So it's always 1 less than j, delta x's to get to the left side of the jth interval. So that is the x, this is the x value at the start of the jth interval. That's why a plus j minus 1 delta x, this kind of confusing expression, goes right there. So a plus j minus 1 delta x is the left side of the jth interval, which is the constant rate of the, which r of that gives you the constant rate for that jth interval. So that's one of the details here, and the other detail is figuring out, other details are figuring out left x and figuring out how many completed intervals we have given x. Okay, let's do, so we'll do left x, we'll do those two details on Friday, left x, and number of completed intervals, and that will also be a reading for 5.2.